Okay, welcome back after your really active Spring Fest. And so let's get back. Now, what I have in the morning part, so it's about half an hour of a lecture on one particular type of a convolution, and then we will again get back to solving your doubts on the coding. So anybody who has doubts and different things which you have tried out and you are still confused around what you did with the neural networks, you can ask that one for the remaining part of the class. Okay, so we will start with something which is called as a vector convolutional neural network. Now, as you get to this one, that there is an additional term called as a vector within a CNN. That's the primary part. Now, this whole thing is something which has to do with the model part of the learning process. It's not with the control plane. So there is no optimization or anything involved over here. It's essentially a different type of a model which handles the data. Now, there is no textbook for this one. There are these two papers from where I'm essentially using my references in order to prepare this material, and this is quite a new one as such. It's a very recent technology. Now, whenever you are trying to solve a learning problem within a neural network, so essentially what you have is something of this sort, that given an image, you have a bank of convolutions, filters. So we also call these set of convolution kernels in a given layer as a bank of filters. It's a very common nomenclature, and you produce a set of tensors over there, and then what you have is essentially a nonlinearity imposed, and then you again convolve and you get some output coming over here. Now, this image may look a bit weird and different, but we will be getting into details about what I was doing in this particular one. As of now, use this as a notional reference. So you can have an input tensor and you can have an output tensor over there as well. And this can also be achieved with a CNN. So it need not always be that you are trying to solve a classification problem. And at the end of the day, what you are trying to do is essentially you find out your error, find out the gradient over the error, and then you solve this part, which is your error backpropagation, for which you need to solve out the gradient of the error with respect to the weights. Okay, great. Now, the challenge which comes down with any kind of a CNN is something of this sort. That say I am training this neural network, this CNN, with in order to just segregate between whether the images belong to that of a house or it belongs to that of a digit or some handwritten number over there. So all images given to this CNN is basically a 32 cross 32 sized image. It's either a picture of a house or it's some handwritten digit over here. Now, when I am training it and then I give it in the same sort of a orientation, so whatever is the upright orientation of a house and upright orientation of a number, then this CNN is supposed to give me a very high activation when it encounters a house, and the CNN gives me a very high activation when it encounters a digit. And essentially you can see that based on the activations which you see on the left hand side, you can pretty much discriminate whether it belongs to the class of houses or it belongs to the class of digits. Now the challenge which comes out is that if I rotate it a bit, then what happens? Now traditionally you would see that for any of your CNNs, you have trained a Lec8 by now, you have trained digit recognition with fully connected networks. Now this is the second part of it. So within your torch libraries you also know about essentially these kind of image manipulation mechanisms as well. So you had used a normalization over there, you had used a 2 tensor conversion, but you can also rotate images inside over there. So just go through the documentation, you will find out. So you can rotate images within with a random rotation within a certain degree. Okay, so plus minus 45 degree, plus minus 30 degree or something over there. Now you can try that experiment. You can actually rotate your images and then feed it to this CNN and then see what is the classification accuracy which comes from. So train a CNN in this way outright and then you rotate all of these and give it. Now the challenge which comes in, the moment you rotate this, then because the CNN had not seen those kind of rotated manifestations while it was getting trained, so it gets into a problem. It's not able to do it. Okay. Now can somebody suggest what can be a way out? So say I want to have a rotation invariant property within a CNN, then how can I get out of this particular problem? Yes. So one good way would be you have all of these upright examples, but then your standard way of data augmentation. So now what you do is that if you want to enable that feature within your CNN, then augment the data by putting in all of those rotations. Essentially you don't need to have that data at source, but you can augment it by putting in all of those distortions into it and then train the network to do this job. This is one way of it. Okay. Can we think of another way? Can there be some other way as well? Think. Can there be some other way? So think of something like this, that convolution as an operation is something which is called as a space invariant, because it's the same convolution operator, same thing which moves over space. Okay. Now, is that rotation invariant? Is convolution rotation invariant? No, no. Can I make convolution rotation invariant? Yes, yes, no. How many of you think that we can make convolution rotation invariant? You can raise your hands. How many of you think we can make convolution rotation invariant? So the vanilla convolution operator will not be rotation invariant, but do you think we can make convolution rotation invariant? Or is there somebody who thinks like we cannot make convolution rotation invariant at all? Okay, good. Only one person, and the rest of you sort of like have no idea. So have you come out of the Springfest hangover yet, or it's still there? I would assume that the rest of the class which is keeping mum is still in that hungover state and continuing till now. Okay, so let's get into what happens. Now see, there are certain properties which are present over there, and these are called as equivariant, invariant and covariant. Now let's understand what these properties of variations are. Okay, and we are looking into something of these properties under this operation called as rotation. Okay, so essentially the point is that say an equivariant point is something of this sort, that say I have an image and I apply some sort of a transformation on the image itself. Okay, so from the image I am deriving an output which comes like this. On the image, if I apply the transformation and derive the output, that is the same as deriving the transformation on the output itself, and then that is what is called as equivariant. So see, I have this whole image over here. You see something gray with some black lines in between. So this is essentially what is called as the scanning electron microscopy image. Okay, so these are small cells, these are nucleus in between, and then you have the cell membrane on the sides over there. And the whole task over here was to segment out the cells from the cell membranes. This is a semantic segmentation task which we are solving over here. Okay. Now, the point is, if F is a CNN which is rotationally equivariant, then what would happen is that if I have this original image and I find out whatever is the output from this by transforming it over F, so that is F of G. So you have something which comes out over here. Now, the next part is that on this same image, I apply a transformation which is G45. Okay, so this is that first part of this left hand side of this equation, which is G on top of the image, and then I take a F. Okay, so that's essentially the image input is rotated, and then I have the transformation applied on the image, and then I get an output which is the same as getting an output which is F on the image and a transformation applied on that output itself. Okay, now an equivariance would state that input and output, both of them vary equally, so they don't have any influence. So whatever is the influence you created on the input, on the output also you will have a similar kind of an influence. This is by definition what is called as a rotation equivariance. Next one is what is called as a rotation invariant. Okay, now in the earlier problem what we were trying to do is a rotation invariant problem in the last slide. So essentially the task was that if I have a rotated version of a digit, still it should recognize that as a digit and not as a house, and it should have an equally high probability over there. So what that means is that if I have an original and I transform and get an output which is F over here on the right hand side, it is the same as I do a rotation on this input and then I do the transformation. So that is F of G. So if F of G of the input is the same as F over the input, then this is what is called as a rotation invariant property. Okay. And the last one is what is called as a rotation covariant property. Now rotation covariant property is something of this sort. Say I have this original image over here, and the task of this network is to find out what is the orientation of this car over here, and that's at 45 degree, so it has found it out. Now if I apply some sort of a transformation, which is again rotate that image by 45 degree furthermore, and then pass it through that network, and then the job is to find out what is the angle, and that is supposed to be 90 degree, which is the same as you have this orientation and you add on whatever is the transformation and you are able to get it out. Okay. So this whole thing will be the same as like transforming the output such that so transformation over this. So essentially this is your f, which is this part, and g dash is this kind of a covariant transformation. So you did not do a rotation by an angle of 45 degree, you added that rotation coefficient over there. So that's a different transformation, which is g dash. Is the same as rotating the image, which is g of the image, times and then operating on the transformation factor f over here, which finds out what is the angle. Okay, this is what is called as a covariant, and covariant essentially means that there are two functions which are varying on a same way, but they are not equal functions. So G45 and G dashed are two different functions. G45 is what rotates the image by 45 degree. G dashed is what basically says that add 45 degree onto whatever is your theta prediction. So they are varying in a similar order, but they are not the same function over there. Okay. Now we need to have these three things clear, and this will help us in finding out what we are essentially trying to derive. Now under certain conditions, an equivariance would mean that you don't have a rotation invariance incorporated, whereas rotation invariance would mean that the convolution operator over there is rotationally invariant, the way it's translation invariant, and covariant would have a similar kind of a connotation as well. Okay. Now we are going to get into what is a rotation invariance operation. A rotation equivariant is what, when we get into semantic segmentation and regression like operations, we will get back onto that. So today's discussion is around invariance itself. Okay. Now here the idea is something of this sort. Say that I have an image over here, which is my input x, and I have derived or learned a convolution block over there, which is this first block, block 1. Okay. Now this block 1 can have, so this block 1 is also what is called as a canonical filter or a canonical represented filter. So a canonical form is basically the primary form of any kind of a filter. That's just what we know about canonical forms, the basic form, the primary form, the original form, whatever you call it. So a canonical form of this one is what was derived in the first initial training. Now what we have done on top of that one is that you can actually rotate each of them with a certain degree, and then create a bank of rotated filters over there. So now if I have a convolution layer which has say 6 convolution kernels, the linear example, 6 convolution kernels. For every convolution kernel I can rotate it, say I decide to do 10 rotations. So the first kernel can be rotated 10 times. So now if I am rotating something 10 times, so between 0 to 360 degree you will have to rotate it by 36 degree. Every 36 degree you rotate, you get down one of it. For the second convolution kernel also you can rotate it like that. For the third convolution kernel also you can rotate it like that. Okay. Now instead of having 6 convolution kernels, I would now be left with 60 convolution kernels in this way, because each canonical form has 10 different rotations which has come over there. Now that you have all of this, what you can do is you can essentially convolve each of them with this original input over here and then get your output. Now this output will also be a set of such things. Now remember, this output tensor has some crazy behavior. So I have say for my first kernel I have 10 different forms of it. So I will stack all of these 10 different forms together over there. For my second kernel I will have 10 different forms of the tensor on the output, so I will stack all of them together. So now instead of being a 60 channel tensor on the output, it's basically a group of 10 and 6 such groups which are present over there. Now this group of 10 which corresponds to one filter has a certain use case over there. Now the way we define them in standard definition is that say if W is that canonical filter over there and G of alpha R is one of those rotations which you had seen in the earlier slide. So this kind of a form, G45 kind of a thing, that is G of alpha R, then it would produce a rotated version which is WR. Okay, and then you can convolve when you get your output, which is YR. Now what we do is, we have this whole set coming down over here. Now the point is, you need to do something which is called as an orientation pooling. Now what this orientation pool does is, say I have these 3 different unique filters over here. Now for each 3 filter I got down this set with R number of channels. Okay. Now over this, what I essentially do is, I try to find out what is the direction in which I have the maximum amplitude, and then I start storing that in terms of rho theta, where rho is the maximum amplitude. So what you would do is, in a given pixel location, in one particular position, across all of these channels which belong to one single filter block over here, you would be looking at what is your maximum amplitude. So at one of these channels you will get your maximum amplitude. Now every channel corresponds to one particular form of theta, which was used for creating that alpha R, G of alpha R. So now for each of them, you know what is your rho theta combination. Rho is the maximum value and theta is that corresponding angle for which you obtain that maximum value over here. Okay. So this whole thing can now give you something which is called as a vector field, and this vector field has a dimension which is h cross w cross 2. 2 in a sense, so h cross w is okay because you will have your height and width over here, and 2 because you have both theta and both rho and theta present over there. So now this is almost like a complex number system representation. So when you have a r theta representation over there. But then remember something, that you cannot match mix all of these blocks together and find it out, because this first vector field is something which corresponds to the first filter block, which was by doing rotations. The second is what corresponds to the second one. The third is what corresponds to the third one. Okay. Now when you go from here, you can do your spatial pooling and everything, and spatial pooling essentially will be on each of them independently. Okay. Now in spatial pooling, what you are going to do is, you are going to retain the theta for which you will have this maximum amplitude present over there. My max pooling is going to operate like that. Okay. You can in fact define something like a max angle pooling as well, where whatever is the maximum angle you can do, but my point is that angles are again a rotationally vague quantity. There is no absolute representation of it, because 0 degree is the same as 360 degree. So instead of 0 degree, something is represented as 360 degree, then your max operation will give you 360 degree itself. So angles are never absolute because it's on a circular scale and it's equivocal, whereas amplitude is absolute. That's the reason why we have this spatial pooling, which is the same as a standard max pooling operator over there. Okay. Now essentially here you would see that there are 2 different kind of operators. One is called as orientation pool, which was to create this vector field from this set of activations, and the other one is what is a spatial pooling, which is the same as a max pooling operation which we have. But then you don't have a standard pooling. You have 2 types of poolings, and which you need to remember over here. Now that you get all of this from here, if I want to look into what essentially happens over here. Okay. Now look into this part over here. So what I get down is that for any kind of a filter, I can essentially represent it in terms of 2 different components over there. One is a horizontal part of the component, another is a vertical part of the component. Okay. Now as I keep on rotating these W's, so these will also keep on rotating over there. Okay. Now if I want to essentially do this back propagation, then you will find out, you can easily derive that whatever is this nabla W, which is the change of wave, is the same as essentially implying the inverse transformation, because you had a G of alpha, which was your forward domain transformation. So if you want to back propagate everything, then whatever gradients come down, you will have to imply all of those in the reverse order. Now essentially through every single channel there would be a gradient which comes down. You invert whatever rotations you had applied, so you will get an output over there. Now whatever is the output which you get, you take an average or just the summation over on top of that. So this gives you your standard average output, which you are now back propagating through the network. And what this is going to update is essentially this first kernel over here, because all these others are not updated. These are just rotated replicas of this first kernel. Now essentially, though it might seem that there are multiple number of kernels and the number of kernels increases, but that's not the case, because these are all which are generated in memory. So you have this kernel which is stored, and all of these are what are generated in memory. So you take that data, you transform, and you just keep it in your local memory for your operation. You are not going to store the whole model over there with all of these rotations going into it. So now, if you look into any standard kind of a problem, then you would be able to see that, say for these kind of semantic segmentation tasks, these kind of rotation ones really work out good, as well as for classification tasks. So this was one of these examples. You can actually try it out, and then this will be one of your assignments where you will have to train a rotated with rotated versions of MNIST. So you have digits, and they will be randomly rotated. Now the challenge will obviously be that a rotated version of 6 becomes a 9, which is a bad case, but a rotated version of 8 is also 8, so that is a very good case. Of a 0 is also a 0. 1 can sometimes get confused with a 7. 7 and 1 will have a confusion in its own way. So they are the challenges, but then still, if you are rotating within a certain degree, so if you say plus minus 45 degree, then you are still in a much more safer zone as such to distinguish between each of them. Now, this was one of these examples where they took a standard CNN, which was essentially a linet, and then you train on MNIST without augmentation, which is you don't rotate anything, you just train it vanilla, and then you look into what is your result with the rotated. So your training set is not rotated, but your testing set has random rotations over there. Now in the testing set, it falters down to 57%. So the accuracy significantly decreases over there. Whereas when you used a rotation equivalent network where you did not have rotated inputs, you gave it straight inputs, but because internally it was able to generate all of those rotated versions over there, so my testing accuracy was still higher over there at 20%. Okay. Now when we go on the other part of it, which is essentially with an augmentation. Okay. Now what this augmentation was doing over here is that you had your standard CNN over there, which was trained, and you had your raw TICnet, which was trained, but then this was trained where your input itself was randomly rotated within a certain angle, which was the same as your output data. And then you can see that like CNN is at about 2.3% because it could learn all of those ones, whereas raw TICnet was even better because the error went down to something like a 1.1% over here. Now on the other side of it, if you look into something where you have a different trunk of the data set called as MNIST raw, where they have rotated it already, and you are training it with that one. So these are these error rates which you are able to see over here. Okay. Now the challenge which comes down is that this is something which we need to realize is what would happen if I don't have rotation equivariant network, but I have a standard CNN and I rotate my input over there and give it to it. So will the same kind of a CNN be able to handle this amount of data, or will I have to increase the model complexity of the CNN? What do you think? Will the same kind of a CNN be able to handle it, or do you think the model complexity has to be increased? Model complexity has to be increased because all of these rotated versions, there will be different kind of wavelet appearances and everything which needs to encompassed over there. However, you are increasing the model complexity at the cost that whatever you have increased over here is essentially redundant because there would be a rotated replica somewhere stored over here. And for that particular reason, rotation equivariant network really comes of use because you don't have to store so much. So your model complexity is reduced, whereas the model capacity does not reduce in any way, and you are still able to train something in the straightforward upright way and then get results which are much more better even in rotated forms as well. Okay. So that's where we come to an end for this one. So there are other forms as well. So one of them is what is called as a steerable filter CNNs, and steerable filters are essentially what you do is that you have your filter kernels over here. So instead of rotating filter kernels, what these guys do is they rotate the outputs over there. So your convolution operation is only done once, and on the output you are just applying that rotation. So it depends on which is a low cost operation for you. For some kind of a process implementation, maybe rotation is a costlier operation than convolution, or vice versa. So based on that you can choose like the first implementation or the second implementation over there. Now you would essentially end up getting the same kind of an output. So these are from two different papers, the first two papers which I had cited, and the objective is the same. The only difference which comes down is either you convolve with the canonical filter and then you rotate, or the other one is where you rotate the canonical filters and then you keep on doing individual convolutions, and then the resultant is still the same. Okay. So this is where we come to an end for vector convolutional neural networks, and that ends my speaking part of the class. So now please, now whoever has whatever doubts in